Welcome to this overview of the Sigma Numerix machine learning vibration monitoring demonstration. In this demonstration, we're going to have a quick high-level view of machine learning for vibration monitoring. We're going to see a demonstration of the trained neural network detecting different vibration modes. And following the demonstration, we're going to provide an architectural overview of the application, and we will conclude with simple instructions for downloading, compiling, and using the SIGLIB machine learning code and demonstration. This slide provides an overview of the stages required for a vibration monitoring application to monitor different vibration modes in a rotating machine. There are several stages to this application, including pre-processing the audio that is sampled via a microphone, in this case for the demonstration, or in most practical applications, a vibration transducer. Following pre-processing of the sampled audio, we can then use that to train our neural network model. And once we have trained the network, we can use the same pre-processing on our sampled audio from our rotating machine to predict the vibration modes of that machine. And following the predictive engine giving us the outputs, we can then pass the results to a fault detection engine to detect faults in our rotating machine. So I'm going to provide a demonstration, and then we will move on to an overview of the algorithms. Just before we start the demonstration, on the right-hand side of the slide here, we have a scatter diagram for the demonstration system. It is a single output node neural network, and the two vibrating modes that we are going to detect are output 0 for a correct operation of the machine, and then output 1, which will be our error condition. And you can see that despite the fact that there is a variety of percentage correct results, the threshold of 0.5 is never actually crossed, regardless of which mode is being used. For this demonstration, we will run in real time on a Raspberry Pi. So here we can see the DC motor, which we're going to energize in a minute, and we're going to sample the vibration modes of the motor using the XMOS microphone array board shown here. And the microphone array board is going to connect via USB to the Raspberry Pi, which is running the pre-trained machine learning algorithms. The algorithms are going to detect one of two vibration modes, which we will call a good and a bad vibration mode, and then they will light the LEDs appropriately. The LEDs will be in one of three states. They will either be yellow to indicate a very low noise energy. They will be red to indicate that a signal energy has been detected, but it is not a good vibration mode. And then they will show green when the energy is detected and the machine learning algorithm has detected that the vibration mode is a good mode. So how do we vary the vibration mode of the motor? Well, what we're going to do is we're going to lift the motor off the table. We will then allow the algorithm to run without me talking, and you will see that it will the machine learning algorithm will recognize that as a correct vibration mode, a good motor running. When I put the motor on the table, hopefully you will be able to hear that there's a very slight increase in vibration. It's only very subtle because I have the foam underneath the motor, and we will be able to see then that the convolutional neural network will detect that the vibration mode is different and the LEDs will shine red. Next, we will go on to look at the algorithms and the details of how they're implemented and how you can download the code off the Numerix website and run the code very easily and train the neural network to recognize different vibration modes for any rotating machine that you care to analyze. Okay, welcome back from the demonstration. Before going into an overview of the application, I just wanted to comment on the loudness of the demonstration heard in that recording. I recorded that prior to recording this section of the overview, and in listening back to that audio, I realized that there was a large difference in the recording between the loudnesses of the two different vibration modes, and I realized that that was due to the fact that the camera and the microphone were mounted on the same table as the motor when I placed the motor on the table. In actual fact, acoustically there was very little difference in the loudness of the acoustic signals. The difference was quite subtle, a lot more subtle than it appears in the video, and shows that the algorithm was very sensitive. In fact, the algorithm works just as well if I had picked the Raspberry Pi up off the table to have removed any possibility of acoustic coupling through the table to the microphones in the Raspberry Pi. Okay, so let's move on to look at the application overview. And this diagram shows the flow diagram. We are sampling the data from our microphones through an analog to digital converter into the thresholding section, which is the section that enables or disables the later processing and linear classification as shown in the LEDs. This section also includes an audio level normalization function to remove any possibility that the trained model or the processing on the live audio is impacted by level differences in the digitized audio. It's purely down to the spectral content rather than the magnitude of the audio. Following threshold normalization, we perform data augmentation, which is a process often used in training to replicate or duplicate audio with different levels of overlap, such that you can use a reduced data set of audio but get a much better trained model for use in our neural network. The following data augmentation in training, we then have the core DSP functions, the Hanning window, the fast Fourier transform, and then the magnitude and dB conversion. Taking the output of the digital data from the magnitude and dB conversion, we then have a one-pole filter for noise reduction, and then we pass the audio into the linear classifier. This slide shows an overview of the multi-layer network. On the left we have our input layer, and these are our frequency domain coefficients. The audio is sampled at 16 kilohertz, and we use a fast Fourier transform length of 256 samples, but we only require the 1/2 of that because of the reflections in the frequency content output of the fast Fourier transform. So the input to our neural network, the input layer, is 128 nodes. Then the data is going from our input layer to our hidden layer, where there are 25 nodes. So we have our cross multiplications, our dot products, which are shown in the different colors, so the blue, the orange and the green, at each of our hidden layers. And then from the output of the hidden layer, we're passing the output to our output layer, which can have an arbitrary number of output nodes. In this particular demo, we just had a single output layer that was just selecting between vibration mode 1 and vibration mode 2. But actually the algorithms can support an arbitrary number of output layers. So that's the overview of the algorithm, the neural network. In terms of the size, and the demonstration that we showed, the model weights are quantized to 8 bits. And this means that the model size is approximately 2 kilobytes plus 500 bytes per additional output category. So in this case, the model is about 2.5 kilobytes. The model required about 2 minutes of audio for training, and on my laptop the training took about 2 or 3 minutes using the data augmentation that I mentioned. The model accuracy is greater than 99%. In fact, I haven't seen it fail at all in the testing I've done, but it is worth noting that the model accuracy for this type of neural network really depends on the similarity or the cross-correlation between the signals that we are trying to detect. Okay, so that's a high-level overview of the neural network. Now let's go and have a look at the process for downloading, building and using the example. The software can be downloaded from the Sigma Numerix website. The URL is shown here, and this includes the full source code for all of the examples shown here. Once you've downloaded the zip file, you can extract it into your installation folder, and then you need to set the environment variables for your compiler, particularly for the header files and the library files that the compiler needs to access. There are example setup scripts available in the root SIGLIBE folder, and more details on this can be seen in the SIGLIBE introductory video using the URL also shown here. Okay, so once you have the library installed, the machine learning examples shown here are located in the examples, so C examples stroke machine learning folder, and the audio files that are used for the training are in the subfolder called original. For this example, there are 2 training files which are provided within SIGLIBE, motor mode 1 and motor mode 2. They're both linear wave files, again 16 kilohertz sample rate. To train the model and validate the model, you need to open a command prompt into the machine learning folder, and then under Windows execute the command shown here, the batch file, or under Linux execute the shell script shown. Either of these 2 scripts will generate a trained file, a series of files, binary format and header formats. So you could take the trained header file, for example, in floating point format, take this header file and then copy it into the example folder where we can then build the real-time application. But it is worth noting that when you run the scripts to train the model under Windows or Linux, that these scripts also run the validation process. So you will see that the validation process will be shown, and you will get 100% validation in your trained model. So if you take the header file that's generated, you then need to copy it into the example folder, and all of the SIGLIBE real-time examples use a audio library called Port Audio. So these examples are stored in the folder called Port Audio Examples. Copy the header file into that folder, and then we can build and run the examples using the following commands. We have a Microsoft build and run batch file, we have a Linux build and run shell script, and we also have one for the Raspberry Pi, which is the one that I was running for the demo today. Actually, it should be noticed that the only real difference between the Linux and the Raspberry Pi shell scripts is that the Raspberry Pi shell script includes a little bit of extra code to drive the SPI LED array as used in the demo. If you don't have an SPI LED array connected to your Raspberry Pi, which is quite likely, then you could just use the standard Linux shell script, and you'll see that the output will be printed to the console. These examples will all use the default audio input device for your computer. Now, for most laptops, the default audio device will be the built-in microphone. In general, these don't give very good results for this kind of application. So if you plug in a high-quality microphone into your laptop or your Raspberry Pi, all you need to do is go into the settings for your computer, your laptop, your Raspberry Pi, and just change the default audio device so that it doesn't use the built-in microphone but uses your high-quality microphone instead. Then you run the scripts and you will be using your high-quality microphone to sample the results. And I'm sure you will get the same results as we saw in the demonstration earlier. Okay, thank you very much for watching. I hope you found this useful. If you have any questions about the SIGLIBE DSP library, in particular the AI functionality or machine learning functionality, please do get in touch, and I look forward to hearing from you. Thank you very much. Bye-bye.